Today I'm going to look at coding routines in C that lets you play a standard MIDI file on the classic Macintoshes from the 80s. If you want to do retro game development on these machines, I think this is a fruitful challenge to tackle. It's a demanding project that makes you dip your toes into file parsing, time management, memory usage, and serial comms. Success in this is gonna set you up for anything involving music, regardless of how it's encoded. MIDI is anything but an obscure format, so there's a huge catalog of music files, as well as documentation out there. Before I do, a reminder that you can actively support modern-day Macintosh retro programming by liking and subscribing to this channel. Thanks! So era number 1 is the one I'm after. It includes the Mac Plus early days in '86 and on. There's no system drivers nor extensions. Early MIDI programs had to use a custom configuration sent to the Zilog serial chip in order to make MIDI communications work at the right speed. I talked about this extensively in this other video a few months ago. Check it out if it's the tricky part you're after. Games like Space Quest 3 exploited this approach for their Roland MT32 soundtrack. Era number 2 started in the early 90s when Apple wanted to create a shortcut for devs and brought out the Apple MIDI Manager. It's basically a software-based switchbox that links your Mac with your external hardware. You can patch instruments and play with channels. I don't know much about it. Apple soon recommended people use third-party solutions like OMS, the Open Music System, from the company Opcode. Free MIDI is another alternative from Mark of the Unicorn. Despite wanting to simplify things, it became a frustrating growing pain period in my opinion. Setting up your hardware and software was anything but a walk in the park in those days. Era number 3, I would say, is when QuickTime joined the party with QuickTime Music Instruments. It added a fully software-based sound synthesis for MIDI. It was no longer necessary to hook up an external MIDI module, although it was still possible to do so and desirable for that quality sound, assuming you had the money. I'm choosing Era 1 because I feel it's the one with no annoying friction point. I don't want users of my apps to have to hunt for drivers or operate specific Mac and system combos. Yes, the learning curve was higher for me when I dealt with the serial communication myself, but once I'm running with it, everything is way smoother for everyone involved. When it's all over, I'll also build a simple file player for System 6. I do think this is adding something missing in our Macintosh garden for this early OS. Your other choices for MIDI playback is to either go hard with full-blown sequencers, or rely on System 7 era programs like Arnold's MIDI player, which came out in the transition period to OS 8. None of these options will do you any good if you want background music in a game you're programming. That's another milestone I'm trying to reach here. I started almost 2 years ago on a modern PC in Python. I still consider myself to be a beginner in that language, but I thought I could create a fast prototype. The main reason why I didn't start on a Mac is that my target platform is the Macintosh Plus, and I want to communicate the MIDI signals into a physical MIDI interface connected to the serial port. I knew it was going to be a pain to get the modem or printer port going. One struggle at a time, please. Phase 1 would look like this, and Phase 2 would look like this. You can get fairly quickly to a kick the tires test with Python for MIDI. This is a piano scale playback code. You just need these packages, time and RT MIDI or real-time MIDI. Turning notes on and off requires 3 bytes every time in this format. The next big step was to parse through the header section of a standard MIDI file. After a lot of reading from classic website sources, remember those? You end up with a clear map of the 14 bytes header. MTHD, the signature takes the 4 first bytes, capital M, capital T, lowercase hd. Then 6, the size is always 4 bytes, showing as 0006. Just detect this and move on. By the way, you can see that MIDI is a format that defines values in a big endian format. The bigger valued bytes come first and end with the smallest one, so you really just get 6 here. If it was a little endian instead, then this would have meant this X value, which is an enormous value. Here you have one of the most important chunk of info, the MIDI format type, and it sits inside 2 bytes. I only really encountered type 0 and 1, and I have yet to see an example of type 2 in the wild, so I haven't bothered with it. The difference in how you approach things with type 1 becomes much more involved than type 0, to the point where it took me months to wrap my head around it. I encountered many dead ends until the final approach settled for me. Next is a 2 bytes number for the number of tracks. Type 0 MIDI files will always show 1 here. Type 1 might show higher than 1. Here's canyon.mid showing as type 0, sporting 1 track. Here's onestop.mid showing as type 1 and letting you know it has hexadecimal 11 tracks, which, if you convert to decimal, means 17. The last 2 bytes of the header are extremely important for how fast everything goes during playback. Here, this would be a value of 255 decimal. It's known as the ticks per quarter note, TPQN. It's also referred to by pulses per quarter notes, PPQ. I'm going to try my best to explain this in a bit. I think it's the hardest concept to grapple for any would-be enthusiast that wants to code stuff with MIDI in it. MTRK, a track has its own signature using 4 bytes. Then this is the number of bytes of data inside that track. Keep in mind that it's in big endian, which translates into 51,365 bytes. However, the devil is in the details. One could argue that the space a track takes in a standard MIDI file is that number, plus the 4 bytes needed to describe the number itself, plus the 4 bytes of a MIDI track signature. The real total is going to be 51,373 bytes. This is important to not mess up in files with multiple tracks. You want to start reading information at the right spots at all times. So far, that's not too bad, right? At this point, all I wanted was to hear something, anything, even if it was not synchronized right. But it turns out you can't be too impatient. This is where it gets tricky and forces you to commit. Everything that sits inside a track is a long sequence of MIDI events. Each event has 2 parts, both are of variable length. There's a time delta part indicating when in the future this MIDI event will happen, and there's a MIDI event command part following that. Then you get both parts again, and so on. A time delta could be 1, 2, 3, or 4 bytes, but it's pretty rare to reach 4 bytes. A MIDI event can also be 1, 2, 3, or 4 or more bytes. These variations in length mean you'll have to code lines of conditional statements and parse through all of that. This does add up in difficulty. It goes without saying that having fixed lengths for both of these would make programming much easier, but you have to acknowledge that it makes sense to use as few bytes as possible for space-saving purposes, especially in the early 80s when MIDI was being designed as a format. Note on in channel 4, note middle C, velocity maximum, but it can also look like this, which means change program on channel 2, instrument 63, which is a synth brass. You have to correctly read all of this and properly digest time deltas before you analyze the next one. Otherwise, you'll get your transitions wrong and all of this will quickly be just garbage. Time deltas are in units of ticks, which means it's not going to be straightforward for you as a programmer. But first, how do you know if it's 1, 2, 3, or 4 bytes long? Just check the most significant bit. If it is set to 1, then you'll have to keep reading the next byte to get the whole value. If that one also has the highest bit set to 1, Well, keep reading. Do that until you stumble upon a byte where it's not set, or you stumble upon the fourth byte, whichever is first. As an example, let's say you encounter 3 bytes for a time delta: XC8, X8A, and X72. First, take the 7 lowest bits of the first one, X48. You can use a mask of 7F to get that, and thus remove the highest bit. Add the masked value to the final pile. Since we're going to read the next byte and find 7 new bits to safeguard, you have to shift the current pile by 7 spots, known as left shifting. Read the next byte, you get 8A. You detect that the highest bit is set, so we'll have to continue on to yet another byte. But first, mask 8A and get the 7 lowest bits. You get 0A. Add this to the final pile. Shift the pile 7 places higher again to make room. Read the next and final byte, you get 72. This time, we know that we have to stop since the highest bit is cleared. Just add this final number as is to the final pile and we're done. This little algorithm takes care of all time deltas despite their variable length nature. So to finally hear something, anything, even if it's a garbled mess that doesn't keep proper time or rhythm, what's left for us to do? We still have to figure out where MIDI commands begin and end, so we need a bunch of if conditionals. The only saving grace is that the MIDI commands are well documented and should be of knowable length fairly quickly. The 1-byte commands are these. The 2-byte commands like change program, which really means change the instrument of a channel, or control pressure and such, are these X codes. The 3-byte commands, which include note on and note off, which decide which musical notes are played, look like this. Then there's a whole category of system common messages, which start with XFF, followed by a byte for the type of message, then followed by a byte telling you how many more bytes are needed for the rest of the command. In this example, you can see a text string description of a track. Once all of this is taken care of, let's recap. 1. Get the generic info from the header. 2. Know where the track or tracks begin and end in the file. 3. Get the time deltas in ticks for each command and what the command is. For a quick test, ignore the time deltas and just push all the commands at a fast, regular interval. After a few tries, I got this. Comically fast canyon.mid. Or comically fast passport.mid. It's bad, but I was happy to get anything out of this. The next logical step is to create the proper delays or gaps between notes, between MIDI events. When we're done, we can hear proper music. We won't be done 100%, but it'll be a good chunk sorted out. You already know about the ticks per quarter note, but the most asked question is, how long is a tick? The answer is frustrating. It depends. You need another parameter elsewhere to figure it out, so bear with me for a few minutes. I'm going to fish out an example from a known MIDI file, passport.mid. Here it uses a TPQN value of 480 in decimal. I read a lot of guides across the internet and I personally found myself more confused after reading some of them. In order to understand what this number means in this context, let's look at just a tiny bit of music theory using music notation. Let's also bring in a simple tune everyone knows, Twinkle Twinkle Little Star. It's in 4/4, so exactly 4 quarter notes for every bar. Let's force it to be 60 beats per minute or 60 quarter notes per minute. 1 bar takes 4 seconds, so real slow. The MIDI file format lives in ticks, so each of these would be 480 ticks. For half notes in that context, you'd need 960 ticks for each, and for a full note, 1920 ticks, and so on. Let's do something more dynamic and add some eighth notes to speed it up. Eighth notes would be 240 ticks. What if you jazzed it up with triplets? Triplets are a third of a beat, so 480 divided by 3 is a nice rounded 160 ticks. Dotted quarter notes to create rhythm tensions. Those are a quarter note plus eighth note and total value, so 480 plus 240 gives us 720 ticks. Maybe you're starting to see that if we want to give musicians maximum flexibility in their note durations, the reference tick value for a quarter note has to be big enough in order to let you compute all of these other note durations. If you need fast passages with 16th notes or even faster, then make sure you can get an integer value of ticks out of it. You don't want to be stuck with floating point values when you divide. That creates rounding errors and your music will just sound wrong. The worst choice you could possibly make is to set a quarter note to be just one tick. You would paint yourself in a corner and you wouldn't be able to use anything faster than that quarter note. So how do you know what to choose? You're free to make other choices that are sensible. If my quarter note was instead 600 ticks, I could get these other values to represent these other notes just fine. Think of the TPQN as a measure of granularity for your quarter notes, and the rule is make sure you deal with integers for all of your needs. Don't pick a needlessly big number either, because you'd force every time delta to use 4 bytes instead of 1 or 2, and this will increase the file size. Getting back to the question, how long is a tick? You can only figure it out if you detect a special meta event, XFF, type X51, which is for meta set tempo, followed by 3, and 3 bytes, so 24 bits of microseconds per quarter notes. Again, let's pick an example from passport.mid. X053B49 is equal to 342,857 microseconds. Remember that you need 1 million microseconds to come up to a full second. This is almost 343 milliseconds, or a bit more than 0.34 seconds per quarter note. How did they figure out that this was the complicated number that they needed? Well, I promise you, composers don't really think in terms of microseconds. They use simpler, friendlier stuff like beats per minute. So passport.mid was crafted with a BPM of 175, which is a relatively fast tempo. Let's do the math. For every 60 seconds, you can fit 175 quarter notes, so each quarter note takes 0.342 and so on seconds, but we rounded at 6 decimal places, hence the number we had. The formula to get this in microseconds is therefore this. 60 divided by BPM gives you how long a quarter note is in seconds. 60 million divided by BPM is the same duration of a quarter note but in microseconds. But in order to deal with MIDI timing in ticks, we need to convert these using our value of TPQN we got from the header. Our example was TPQN equals 1 quarter note equals 342,000 microseconds equal 480 ticks. How do we use this? We compute how many seconds we need to wait for any single tick. So 1 tick here would be equal to 714 microseconds. Let's add that last conversion to the final formula. Microsecond value of a tick, 60 million divided by BPM times TPQN. Remember to stick with these parentheses in the denominator to calculate this properly with the order of operations. With this, you can finally figure out how long to wait according to the time delta values you're reading off from your MIDI file. Get a tick value, compute the microseconds you need to wait before doing the MIDI event, rinse and repeat. If you do any amount of retro programming, you know that integer math is fast and floating point math is slow on these old processors. This is a potential area where we might need optimization if we catch slowdowns or something. In fact, I was so afraid of these in advance that I set up to calculate the ratio between ticks and microseconds using floating point division once. Then every MIDI event is simply a multiplication. But it turns out this created a critical bug in my player. I'll tell you why in a moment. But first, let's hear Canyon.mid with proper timing now. First, some files will not have a meta set tempo event at all. There is a MIDI known default tempo of 120 BPM if nothing is specified. This means your player has to assume an initial value of 500,000 microseconds per quarter notes. That's an easy solve. Second issue is a bit more involved. Set tempo is an event that can easily happen multiple times over the course of a playback. That forces you to do our formula as often as it comes around, even if it's a dozen times. One notorious example known for its complexity is OneStop.mid, which features different styles like jazz, rock, cinematic, and more. They each will set their own tempo. While the TPQN value is only set once, the conversion of that tick into microseconds will be continually updated. In Python on my modern PC, I'm not too concerned about doing these divisions and multiplications on the fly. On a Macintosh Plus, though, I'm worried. That's a bridge to cross for later. The biggest problem that threw me off for several weeks, though, was related to Type 1 MIDI files. Remember that this means multiple tracks, which are listed sequentially inside your file. When you open up OneStop.mid, you have to worry about 17 tracks. By the way, you end up noticing that track 0 often takes the role of just having a bunch of setup meta commands that affect things in general, like reverb and tempo. The actual musical data is stashed in the other tracks. Instead of having these events in order in a one-track file like you get with Type 0 MIDI files, you get these intertwined events with just 2 tracks, let alone more. You might get 3 events happening in track 0 while track 1 is set to act later. You might have 100 pitch bending happening with an electric guitar in track 5 while track 6 does a slow, steady beat. The big problem is that you're responsible to parse through all of these tracks and do the ordering yourself with code. Type 0 files with just a single track are easy enough. Read the next MIDI event, do it right away if the time delta is 0, move on to the next one until the song is done. For Type 1 though, you need to pit all the tracks against each other and figure out which one must be done ASAP. It's kind of like trying to serve people in a packed restaurant and serving the priority clients in the right order in multiple tables, then come back for follow-ups, taking away empty dishes, and so on. My fear at this point was I don't want to keep jumping around my open file. I'm afraid file access is going to be slow on a Macintosh eventually, so let's stash all of this stuff in RAM, but let's also parse it in advance so that I don't have to do a costly bunch of conditional checks. Remember, I've never done this kind of real-time music file player before, and I'm not a professional programmer. My mind was swimming with ideas and not necessarily good ones. My first approach, create a data structure for a MIDI event containing both a time delta and an array of MIDI bytes containing the command. I would create a TOE, or table of events, to group them together. Each track would get its own toe. I would only keep events that are directly affecting what you hear and discard optional stuff like track description text strings. During my playing loop, when I need to evaluate what event to do next, I just sift through every toe and do the 0 time delta ones right away. If it turns out the very next event right after the one I just processed is also a 0 time delta one, do it right away too. In fact, you'll get a bunch of events stringed together occasionally, while all the other tracks must wait patiently. I do this until I encounter an event which is requested in the future with a non-zero time delta. When this happens, let the tracks compete against each other and find the lowest one and do it. When it's done, lower every pending event by that tick amount. This way, the priority for every event increases as time is chipped away. This algorithm seemed reasonable enough, right? And you know what? When I finally landed on this, after bug hunting and dead ends avoiding, it sounded nice, but I didn't like it. It had a really annoying flaw. You see, populating those TOEs requires a lot of time up front while you load a standard MIDI file. We're talking fractions of a second on a modern PC, but for the Mac Plus, it can grow to several dozens of seconds. File access is slow, and creating this big array of structures is slow. Second approach is copy the whole MIDI file into RAM as is, but keep one RAM pointer for each track. When one MIDI event has been processed, make the pointer advance to the next event, then reevaluate your event priorities. MIDI files are very often under 100 kilobytes, so that's very doable even on a stock 1 megabyte Mac Plus. File access only happens during the loading of the data into RAM, and you just accept to update the microsecond per tick value whenever set tempo event happens. In the 80s, space-saving measures could be found everywhere. MIDI files were no exception. Even though they are considered absolutely tiny today, in the days of 800K diskettes, there was a need to make this data as compact as possible. That's why if the MIDI file is about to repeat a command twice in a row, the data can be made to remove the byte that identifies the command and go straight to its information bytes. For example, if you're about to send a middle C with maximum force on channel 0, you'd write it as time delta followed by X9E, X3C, X7F. If you want to do another note on right away in order to perform a chord, you could send it as a time delta X9E, X3D, X7F, which would layer on a D note on top of the C note. However, if you want to save that extra byte, you can remove the second X90, which merely indicates to perform a note on command a second time. But how does it work exactly? It's simple. Commands are guaranteed to have the most significant bit set. You'll never find a command that doesn't have the I nibble equal to 8 or more. These are the only possibilities that mean you're getting a command. Meanwhile, when the program receives one of these after the timing delta, your program has to treat them as a data part and has to recall the last performed command. Saving a byte once in a while is not that much to write home about, but it can happen hundreds of times in a song, and when you multiply it by the number of songs, you start to realize it makes sense. And we get to a final problem. For some reason, a few programs or hardware sequencers back in the day never sent X8N commands to indicate a note off. Instead, they decided to send note on with 0 velocity, which could look like this. And if we apply the trick in the previous section, it can even look like this. I'm guessing the ability to combine both note on and note off into a single command is the space-saving measure being at work here. This can help squeeze just a tiny bit more space in this era of starvation of storage solutions. I was confident to port my working Python code to the Mac at this point, but I knew it wouldn't be a walk in the park. Still, the hard part of figuring out the MIDI file format spec was behind me. Here are the parts I needed to assemble together. 1. Let a program bring up the standard file picking dialog, something I've done in the past. 2. Set up the modem port for MIDI speed, done and explained in a previous video like I said. 3. Parse the MIDI file to find out the track count, TPQN, and optional stuff like track names. 4. Do a loop and visit the pending events once in a while. 5. Send off the events that matter only to MIDI hardware. 6. Use the proper Macintosh time manager routines from the standard Mac libraries to manage microseconds properly. 7. Make a dedicated simple playback program with a nice icon and options. I added all of these ported routines to this MIDI test bench program I used in the past to drive real-time MIDI stuff. However, I was still creating big data structures for no real gain at first, because I didn't know better. But getting to a point where it more or less works is a huge boost to my confidence. You can hear the slowness of my code with doom.mid. These tracks are brutal in terms of MIDI event density and will bring any subpar algorithm to its knees. When I switch over to the other approach, load the file wholesale into RAM and just use the one pointer per track strategy, and here's the playback. Okay, that's great and all, but can this be part of a game engine? Can we let the Mac deal with graphics and inputs in real time? The answer is emphatically yes. Exactly like Sierra did with their Mac port of Space Quest 3 back in 1991 using a Roland MT32 soundtrack. My code can easily do the same now. I basically reverse engineered a Macintosh hardware MIDI driver. So I present to you a brand new app in 2026 that packages all that I've learned on MIDI playback and that can run off of a Mac Plus. It requires a hardware MIDI interface and a hardware MIDI module, both of which there are plenty of options nowadays. I'm calling it cozyMIDI, and I released it a few days ago on Macintosh Garden. It isn't anything groundbreaking, but it lets you play a file outside of a complicated music sequencer. I'm not promising the fastest code, but it does work. If you're interested by the C source code as well as a Python script that I have, be sure to check in the links in the description. The background image was done by me last year in MacPaint, an image I sent out to the fine people of Global Talk 2025. It also has this icon I made in ResEdit, a musical note being cozy on a couch. Once I finish adding a key feature, playlist playback, I'll make a small demo video of it soon. That's gonna be it for now. Thank you for watching until the end. Since you stayed until the end, I recommend you also watch my video on FireJam, where instead of digesting and playing a MIDI file, I let my code react in real time to the presses of a MIDI piano controller. This turns your Mac Plus into a synth. Please check it out, and I'll see you next time.